This unit is all about chemical bonds. This particular video will focus on these two learning targets. I can distinguish between general ionic and molecular properties, and I can describe the process of ionic and covalent bonding, okay? How they happen, kind of the nuances of the actual bond. So when we're talking about bonding, what is a bond? Okay, what are we talking about? Well, essentially, a bond is a force that's holding elements and atoms together. If we think all the way back to chapter 1, we talked about elements and atoms, we talked about mixtures, and we talked about compounds. And compounds were the chemical combination of two or more atoms or elements. Okay? How do they come together? Well, essentially, they come together through a bond. Okay? The bond is the force that's holding the atoms together. And whatever this bond is, it's got tons of energy. Okay, there's an actual measurement called bond energy, and it's the energy that you need in order to break a bond apart. Okay, when they come together, they are very stable. Okay, I've told you there's always two kind of driving forces for matter. One is to be neutral, and one is to be stable, to have that full S2P6. And so the driving force for bonding is that you don't have S2P6. So somehow you're still going to stay neutral, but fill that valence shell to S2P6 because that is more stable. There's two types of bonds we're going to look at for compounds, ionic and covalent. Let's start with ionic. Cut and dry, what an ionic bond is a bond that's created when you transfer electrons from one atom to a new atom. How do you get more information about that? Well, basically the driving force here again is those outer electrons to be S2P6. Okay, that's the octet rule, and we'll talk about the octet rule a lot. So if you count S2P6 together, you get 8. So 8 electrons is the driving force for ionic bonding. What electrons will be doing this? Those valence electrons. So the outermost electrons that exist beyond your nearest soluble gas, those are the electrons that will be doing the ionic bonding. So they have to undergo some kind of electron transfer. And here's how it works. When you have two atoms come near one another, one that has a high electronegativity and one that has a low ionization energy, when they get near enough, the one with a high electronegativity can essentially rip an electron away from the atom with low ionization energy. So you have a physical transfer of electrons from one atom to a new atom. Okay, it's a physical transfer. Now what's funny about ionic bonding is I always think of it very different than covalent bonding. Okay, I'm going to personify our elements again, and I often talk about them like a relationship. When these two atoms came near one another, one of them had something the other one wanted. Okay, and the element that had a low ionization energy and was willing to give up an electron was like, sure, take my electron, that's totally fine. But they weren't entering into a relationship with one another. One of them was going to physically take the other electron. Now, the reason why it ends up creating a bond is about the charge attraction. So essentially it's like one atom saying, here, take my electron, the other one being like, okay, great. And then once the electron transfer happens, they're stuck together. That's from this picture. So magnesium and oxygen come along. Oxygen is the more electronegative, and it's like, hey, magnesium, you have electrons I want. And magnesium's like, sure, go ahead, take my electrons. That's awesome. I don't want them, right? If you take them, we have the S2P6 happening. So we have the electron transfer happen, but now those two atoms are no longer independent. Because when oxygen took on the two negative charges, it became negative. When magnesium lost the two negative charges, it became positive. Opposites attract, and those two atoms, while that might not have been the intention, are now stuck together. They are bonded by a force of attraction. There's no physical connection between them. If you see here, they're two separate atoms. They just have a force of attraction to one another, keeping them near each other. Okay? So the ionic bond is not really a bond per se. It's an electrostatic attraction. It's a charge attraction that exists between the two atoms. So one thing you have to understand is how they come together in order to create that stable electron configuration. So here's a picture. If sodium and chlorine come together and want to transfer electrons, sodium wants to give up one and chlorine wants to take one. So just one sodium and one chlorine come together will form a nice ionic bond. Now calcium also wants to give up electrons and chlorine wants to take them on. But here we have a slightly different situation because calcium wants to give up 2 and chlorine can only take on 1. So calcium can't force chlorine to take on 2. But there is still an ionic bond that can happen between calcium and chlorine. And the deal here is it's just not a ratio of 1 calcium to 1 chlorine. It's a ratio of 1 calcium to 2 chlorines. It's a 1 to 2 ratio. So the ionic bonding can still happen and the force of attraction will still happen. But instead of it just being 1 and 1 atom, we have 1 and 2. That's totally fine and acceptable. Okay? So when you're trying to predict how ions will form bonds, it's all about their charge. They're coming together and they have to transfer enough electrons to satisfy each other's octet. So the ratio will not always be 1 to 1. For example, let's say we had, instead of calcium and chlorine, we had like oxygen, which likes to form a -2 charge, coming together with something like sodium, which likes to form a +1. To have these two things bond then, it's not just NaO, because you have an overall net charge of -1, because oxygen can only get 1 electron from sodium. So instead you need 2 sodium atoms coming together to bond with the oxygen. And that's how you show it. The subscripted number here says how many you have, okay, how many of each atom you have. So that's how the bond is formed. What properties you have to know about ionic compounds are given here. They're hard, and they make something called the crystal lattice structure. So I'll show you this actually in class, but the deal is, opposed to compounds, when you make an ionic bond, you don't simply have, like in this example, 2 sodiums and 1 oxygen, but you actually form something called a crystal lattice structure. So you actually form some kind of network of molecules that are all together in a clump. So ionic compounds form like a really big crystal, and I'll show you this in class, but you just need to memorize that ionic compounds form a crystal lattice structure. These, when dissolved in a solution, can conduct electricity, because when they're dissolved in solution, what they do is they fall apart into their ions. And what electricity is just moving charge. So once you have ions available in your solution, those ions can travel, and thus you have moving charge. They have very high melting points. Remember, when you're melting something or boiling something, what you need to do is produce space. And these aren't just intermolecular forces, which I've mentioned before. These are full-on opposite charge attraction. So for you to get enough energy to actually like break this apart, it's a lot. It's a lot of energy to try to get that thing apart. So they have very high melting points. Because of the crystal lattice structure, you can't really articulate exactly what's in this gigantic crystal. How we report the composition of the bonds is we give ionic compounds something called a formula unit. And what a formula unit is if I looked at this gigantic structure of sodiums and oxygens and looked at the ratio between sodium and oxygen, it would always break down to 2 sodiums per 1 oxygen. Okay, so this is a formula unit. It's the smallest ratio of atoms within your crystal. Okay, so when ionic compounds come together, when nonmetals and metals come together in this bond where they transfer, they're not just a ratio of a few in a molecule. You're used to seeing like the water molecule, which looks something like this. Okay, that's an actual entity to itself. It's not bonded to anything else. Or for ionic, they're kind of a conglomeration of all of these. So for example, sodium chloride actually actually looks like this. It's a crystal lattice. There's not just one sodium and one oxygen all bonded together. There's all of these atoms together in a clump. And I'll show you models of this in class. So that's ionic compounds, where you transfer electrons. Now, what do your parents say if you and your sibling both want the same toy? They probably tell you to share. And that's the other type of bond we have, is a sharing bond. So a single covalent bond is simply the sharing of two valence electrons. Okay, one bond contains two shared electrons, an electron pair, right? What's going on here is right here, is that two atoms that are both really high electronegativity, meaning they both can attract electrons to themselves really well, come together, but they can't transfer, because one of them's being like, I can pull your electrons, the other one's like, I can pull your electrons, and all the two of them are like, what do? We both would like electrons, but neither one of us is willing to give them up. So instead, it's like they enter into an agreement where they share. Some people use the analogy of marriage, in that these two things come together and they're going to share an existence and their electrons rather than simply taking them. Now it's different because they form molecules. A molecule is a defined composition of what atoms are bonded together using covalent bonds. The formula for the molecules is not always the most reduced. It's the literal, written down what is bonded together. Okay, for ionic, we don't literally write down what is bonded together because it's a big conglomeration, and all we really want to know is what the ratio is. For covalent, it does matter what actual atoms are sharing electrons. Okay, so it's not a formula unit, it's an actual molecule. So this is kind of what it looks like to share electrons. Right? Those two red dots are the nuclei, and the blue is the electron cloud. They're actually merging their electron clouds together to form a bond. And where that E is on the screen, that is your bond, shared electrons that reside between the nuclei of two adjacent atoms. That is a covalent bond. If you look at electron configuration, you can also see how this works. So if two fluorines are going to come together to make a covalent bond, basically they have S2P5. Two of their P5s are literally going to come together, and that extra P orbital right there is going to overlap and merge to make one orbital where those two electrons reside. So you have a recombination of orbitals also when you go into covalent bonding. Properties of molecules or covalently bonded elements. It's a formula. Okay, the actual elements that are bonded together, that's no crystal, there's no formula unit, nothing like that. It's just a molecule. These are all produced by metals bonding with metals because they have to be really high electronegative atoms. They have relatively low boiling points, a lot of them. In fact, some of them are gases at room temp, right? And they're non-conductive, generally speaking, or very low conductivity if they can conduct at all. Okay? So that's your video on your properties. We're going to do a lab where we actually identify whether you're working with an ionic or covalently bonded compound based on properties.